sorry about that, just some technical difficulties. So let's continue where we left off. So now we have the limit as n approaches infinity of 1 over n cubed times the sum 1 squared plus 2 squared plus dot 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 plus n squared, right? I factored out the 1 over n cubed from each term and got that. Right, so now we need to find the sum of the squares from 1 to n. And so there's a formula that will help us with that. 1 squared plus 2 squared plus dot 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 plus n squared is equal to n times n plus 1 times 2n plus 1 over 6. Okay, so the sum of the squares from 1 to n is equal to n times n plus 1 times 2n plus 1 over 6. And so I'm just going to substitute that in here. So I'm going to write the equal sign over here now. This equals this to give myself space. This is equals to the limit as n approaches infinity of 1 over n cubed times now n times n plus 1 times 2n plus 1 over 6. So I'm just substituting the sum of the squares there for that. And so now I'm going to move the 1/6 out of the limit. And I'm going to have 1/6 times the limit as n approaches infinity of the rest. But now, if you see the numerator here is n times n plus 1 times 2n plus 1, and I have an n cubed in the denominator here. I'm going to separate the n cubed in the denominator as n times n times n. I'm going to take each of those n and divide them correspondingly by each of these 3 factors correspondingly by one of those n's. So you get the limit as n approaches infinity of n over n times n plus 1 over n times 2n plus 1 over n. And so it's not only it has to happen in order to compute this limit that the number of n's I have here are the same as the number of factors I have there. If there were not enough n's here, if there were only n squared, you would go to infinity. So, but we have exactly 3, and that works perfectly. So each of these factors, I divide by one of those n's. I get 1/6 times the limit as n approaches infinity of n over n times n plus 1 over n times 2n plus 1 over n. And the limit of a product is a product of the limits if each limit exists. And n plus 1 over n is 1 plus 1 over n. 2n plus 1 over n is 2 plus 1 over n. N over n is 1. And so this is equal to the limit. So it's limit that. This is equal to 1/6 times the limit as n approaches infinity of 1 times 1 plus 1 over n times 2 plus 1 over n. This is equal to 1/6 times the limit of 1 is 1. The limit of 1 plus 1 over n is 1 plus 0, which is 1. The limit of 2 plus 1 over n is 2, which is... So 1/6 times 1 times 1 times 2 is 2/6, which is 1/3. And so now the limit of n as n approaches infinity of r sub n is equal to 1/3. Okay? And so we just calculate this limit as being 1/3. And we use this formula. 1 squared plus 2 squared plus dot 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 plus n squared equals n times n plus 1 times 2n plus 1 over 6. And so now we have that formula to use in this problem. Okay? And so in this example, we have actually infinitely many approximating rectangles, and we took the limit of their sum, and we got 1/3. And 1/3 is actually the actual area under the graph y equals x squared from 0, x equals 0 to x equals 1. The area of that shaded region is precisely 1/3. Okay? We haven't gotten into why doing this gave us the actual area, but we will. Okay? So let me point out something else. Okay, so in that example, we use the formula 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared equals n times n plus 1 times 2n plus 1 over 6. And that's an important formula to use for these type of problems, the limit of r sub n or limit of L sub n. Another important equation is 1 plus 2 plus 3 plus dot 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 plus n. That's equal to n times n plus 1 over 2. That's another important formula. And then another important formula is 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus n cubed. And that's equal to n times n plus 1 over 2, that entire thing squared. Okay? And so those are three important formulas that you'll need for this section. Okay, so I just inform you that now. Okay, so you'll need those three formulas to compute these kind of problems. Tiny answer these kind of problems. Right? And so for this lesson, we went over antiderivatives and we went over approximating rectangles. Okay, next lesson, we'll be talking about computing, more about how we formulate the definition of an integral and how to find exact areas of regions using the integral. Okay, so we'll go on to that as we go deeper into this chapter. Okay, so thank you for watching the first video, and I hope you enjoy the semester. And I hope it's not too hard to use Blackboard, and I'll see you next time. Bye.